Hello friends, today we'll solve the GATE 2024 Digital Electronics problem of Electronics and Communication paper. So this is the first question. It is saying that for the Boolean function f a b c d, so there are some terms given. We need to find essential prime implicants. So for this problem we need to make first of all k-map. Okay, so this is the k-map a b c d, and then we fill this at 0 0 0 1 1 1 1 0, then simply here 0 0 0 1 1 1 1 0. So these are gray code, and then if fill them as 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. Now simply we put one wherever the minterms are there. So 0 2 5 7 8 10 12 13 14 15. So 0, and then it's like 2, then it's 5 7, and then it's like 8, and then it's 10, and then it's 12 13 14 15. Okay, then second step is to first of all make all possible best groups. Okay, so these are called as prime implicants, so all possible best groups. So here we can get one quad, here we can get one quad. Okay, this outer also we can get one quad, and one more quad is there like this. Okay, so total 4 groups are getting, so 4 prime implicants. Now essential prime implicants are those prime implicants in which there is at least one element which cannot be part of any other group. So here you can see that this one can only come in this quad, and this one also can come only in this quad, so this is essential prime implicant. Similarly this one and this one can only come in this external quad, so this is also essential prime implicant. This cannot be essential prime implicant because this one is coming in two group, this one is coming in two group, all 4 are coming in this group also, this group also, this group also. So only 2 essential prime implicants will be there. These ones cannot also be make a essential prime implicant because this one is coming in two groups, this one is also coming in two groups. So 2 essential prime implicants, this outer chord and this inner chord. So outer chord have, to find this we can write it like this: coordinate has 0 0 0 0, this has 0 0 1 0, this has 1 0 0 0, and then this has 1 0 1 0. Okay, so we take the common thing, so common here is 0, common here is 0, so this is b bar d bar. Okay, similarly for this one we have this one we have like 0 1 0 1 0 1 0 1, this has 0 1 1 1 0 1 1 1, this has 1 1 0 1 1 1 0 1, and this one has 1 1 1 1. So the common thing is b, and then here it is b, so bd. So bd and b bar d bar is the essential prime implicants. Okay, second question is on priority encoder. Okay, so here it is saying that a 4-bit priority encoder has inputs d3 d2 d1 d0 in descending order of priority. The 2-bit output ab is generated as 0001 1011 corresponding to d3 d2 d1 d0. So the boolean expression of output bit b is. Okay, so first of all we need to make the table. Okay, so this is maximum priority is d3 and d1 as least priority. It's a 4-bit priority, and this is the output. Okay, so d0 d1 d2 d3 we write it like this. So when d3 is 1 or high, it doesn't matter whether these are 0 or 1, output is 0 0. Okay, similarly when d2 is 1 and these two are don't care, obviously this has to be 0, then output is 0 1. This is given to us. Similarly if only this is high and this is don't care, then we get this thing, and when only d0 is high, then we get 1 1. But there is a fifth case also which is should be given, but it is not given. That what will happen when all bits are like 0 0, then since nothing is given, so we can treat it as don't care. Okay, so without this the options will not match in when we solve it using k-map. Okay, So we will take it as don't care, and now we will make k map. Okay, d0 d1 d2 d3 like that, and we will take this b bits as 1 1 for the case 0 1. Don't care means this can be anything. So the case where d3 d2 is 0 1, so d3 d2 is 0, d3 is basically here 0 and d2 is 1. So d2 is 1, and d3 is 0. So this is the case, and d0 d1 can take any value. So this is one quad. Okay, and in this case what is happening is 0 0 0 1. So d3 d2 is 0 0, and d0 is 1. So and d1 is 0. So this is the one, and all for a this is don't care, so we'll take it as 1 also. Don't care means we can take it either 0 or 1, so we'll take it as 1. Okay, so this one external chord will be there, and this chord will be there. Okay, so this chord is clearly d2 d3 bar. Okay, and these four will be like you can write them as this as d0 bar d1 bar d2 bar d3 bar. Okay, and this one as d0 d1 bar d0 d1 bar, and then d2 bar d3 bar. Like that we can make all four of them. So common part is d1 bar d3 bar. So d1 bar d3 bar is there, so d1 bar d3 bar is there, and this part is there. So output expression for b is this thing, b option. Okay, you can see the truth table, and you can also see the k map. Okay, so again easy question. Third question is on mux. It is saying that the propagation delay of a 2 into 1 mux shown in the circuit is 10 nanosecond. Consider the propagation delay of the inverter as 0 nanosecond. So if S is set to 1, then output Y is a square wave of frequency 100 Hz or 50 Hz, constant, or constant is 0, constant 1. So let's say it is 1. Okay, then it will come here, and 1 will come to 0. Okay, then this 0 will come here. So since this select bit is 1, so this means this thing is shorted to this part. So whatever will come here will come here. Okay, so uh, this 0 will come here. Now again this 0 will come. Okay, then through inverter after 0 nanosecond or no delay it will become 1. Then again this 1 after 1 nanosecond will go here. Okay, then again it will go, then 1 will turn to 0, and then 0 will turn to 0 will after 1 nanosecond delay, this 10 nanosecond delay, it will become 0. So you can clearly see it's 1 0 1 0. It will happen after every 10 nanosecond. So if it is 1, then after for 10 nanosecond it will be 0. For again like for 10 nanosecond it will be 0 1 then 0. So this will happen. So you can see that one time period is 20 nanosecond of the output. So frequency is 1 upon time period, so 1 upon 20 nanosecond. So okay, so 20 nano, so 20 into 10 raised to power minus 9, so it will go up, so it will become 10 to power 9 upon 20. Now we need to find the answer in megahertz, so we can write it as 10 ki power 3 into 10 ki power 6, which is megahertz, and 1000 upon 20 is 50, so it will be 50 megahertz square wave. So B is the correct answer. This question is on flip-flop. It is saying that the sequence of states Q1 Q0 of the given synchronous sequential circuit is, we need to find the sequence of state of Q0 Q1. So it's a straightforward sequential circuit problem, synchronous counter problem. So both because both flip-flop are governed by same clock. Okay, so for all such questions what we do is we make a truth table. We make this table which is like present state, flip-flop input, next state. in present state we write q1 q0. We write q1 q0 because this is given in this form, so we will also write it as this form, q1 q0. And then since it is q1, so we'll write t1. Input of flip-flop 1 is nothing but q1, and then this thing is q0 bar, so q1 plus q0 bar. Similarly this one has q0 and then q1, q0 and q1. Okay, and next state is q1 plus q0 plus. Okay, so this next state is like that. Okay, so now we start with 0 0. Okay, and so for 0 0 it will be like 0 plus 0 bar, so it is 1. It is 0 plus 0 is 0. Okay, so basically you can see that t1 is in toggle mode. So if t flip-flop, you know that if t input t is 1, the next state is complement of previous state, and if t input is 0, so next state is previous state only, because t means toggle. So if toggle uh, button is on, so it will invert the previous state. So here since t1 is 1, so it will invert it, so it will become 1. But t0 is 0, so it will not invert the previous state, so it will become 0. Now this 1 0 will come here. Now you can see that t1 is nothing but q1, which is 1 plus 0 bar, so 1 plus 1 is 1. t0 is 1 plus 0, again 1. Now both are in toggle mode, so both will invert, so 1 will become 0, 0 will become 1, so we come to 0 1. Now you can see that t1 is 0 plus 1, 0 plus 1 bar, so it is 0, and t0 is what, sum of both, so it will be 1. Now this is not in toggle mode, so it will keep the previous state, whereas this in toggle mode, so it will invert the previous state, so it will become 0, so it is again becoming 0 0. Okay, so we are again getting to previous state, so again same thing will go. So basically you can see it will be go like 0 0 1 0 0 1, then again 0 0. So 0 0 1 0 0 1, and again 0 0. And what if, let's say, somehow the counter goes into 1 1 state, then what will happen? t1 will be 1 plus 1 bar, so it is 1, and t0 is sum of both, so it will be 1. So both are in toggle mode, both the t flip-flop, so it will invert both of them, so it will be 0 0. So even if it is in 1 1, it will go to 0 0, and from 0 0 it will go to 0 1, and then 0 1 to 1 0 to 0 1, then again like that. So this is the correct answer to this question. So all such questions can be easily solved using this table. Okay, fifth question is on A to D converter. It is saying that a full scale, let me zoom in. A full scale sinusoidal signal is applied to a 10-bit ADC. The fundamental signal component in the ADC output has a normalized power of 1 watt, and the total noise and distortion normalized power is 10 microwatt. So effective number of bit of the ADC is. So here we need to involve two formulas. So it is basically asking about SNR of an ADC. So first of all, by definition, SNR is signal power to noise power. Now signal power is given to us as 1 watt, and noise power is given to us as 10 microwatt, which is 10 into 10 to the power minus 6. Okay, so it will go upward, so 10 to the power 6 divided by 10, so 10 to the power 5. Now we need to convert it in dB. So for converting in dB, or if power is given, so we use 10 log 10 signal power upon noise power. Okay, otherwise voltage or amplitude was given, then we need to use 20 log 10 signal power upon noise power. So we will use this one because this is power, so this is 10 log 10 10 raised to power 5, so which is 50 log 10 to the base 10, so which is 1. Okay, log a to the base is 1, so this is 50 dB. Okay, so now we will use our main formula, that SNR of the general ADC is 50 dB and is equal to 6.02 n plus 1.76. So n is equal to what? 50 minus 1.76 divided by 6.02, which is 48.24 divided by 6.02, so it is 8.01, which is almost equal to 8. Okay, so 8 is the correct answer. So this n is like number of bits of the ADC, or effective number of bit of the ADC, or even resolution of the ADC. So for all SNR related problem, this n can be given different name in different years. Okay, so this was again easy. So these were all 5 questions of digital electronics. Thank you.